Okay, welcome to lecture 39. We're still talking about numerical methods for ODEs. So in this lecture, we'll continue to discuss the improved Euler method. So we'll look at the truncation error and the global error in the improved Euler method. And we'll also look at some examples plus some Octave or MATLAB examples too, because really we don't want to calculate all these things by hand because, well, it's tedious, whereas a computer can calculate these things in seconds. Right? So this was a summary slide from the last lecture here. So we had, for all the methods that we've looked at, the last two lectures, we have this discretization of the independent variable x. So we discretize x into multiple steps. And then we had three different methods: Euler's method, the trapezium method, and the improved Euler's method, to update our approximation of y at these points xn. Okay, and so today we're going to be focusing on the improved Euler's method, which, if you recall, was called a predictor-corrector method. And the reason for that is that we use Euler's method, this first step here, to calculate an approximation to y of n plus 1. Okay, and we're going to call that approximation yn plus 1 star. And then once we have that, we're going to approximate the actual value of yn plus 1 using this formula here. Okay. So the local truncation error of the improved Euler's method, this error E, is less than or equal to 1 over 6 times m3 times h cubed. So this is why we said in the previous class that the improved Euler's method has a local truncation error of order h cubed, because the error scales with h cubed here. Okay, so if I half the error, if I half the step size h, I get 1/2 cubed, which is 1/8. So I get 1/8, an 8 times reduction in the error if I half the step size. This thing m3 here, this is the maximum of the third derivative of the exact solution on this domain xn to xn plus 1. So we'll come back to this a little bit later. But for now, I should also say that the global truncation error of the improved Euler's method is order h squared. So if we half h, so if we half the step size, then we reduce the global error by 4 times. So that's, it's 2 squared. So let's look at an example now. So we have the ODE, y prime is equal to x minus 2y. We have the initial condition, y, when x equals 0, y equals 1. Okay, well, we can show, in fact, you can show that the analytical solution to this ODE is 1/2 x minus 1/4, to this initial value problem, in fact, it's 1/2 x minus 1/4 plus 5/4 times the exponential of negative 2x. Okay, and we want to imply, well, firstly, Euler's method, and then the improved Euler's method with a step size of h equals 0.1, and we just want to use one step, just to get an idea of how more accurate the improved Euler's method is over Euler's method. So the original Euler's method is quite simply, the update for yn plus 1 is yn plus h times the function f evaluated at xn yn. Okay, so remember, the function f is just the right hand side of the ODE. So the function f is x minus 2y. So if I evaluate that at xn yn, then f xn yn is xn minus 2 times yn. Okay, the improved Euler's method, though, this is our predictor-corrector method. So the first step is to calculate yn plus 1 star, which is exactly the same as taking one step of the Euler's method over here. Once we have that, then we evaluate the second line here, where we have yn plus h times the function x minus 2y evaluated at xn yn plus the function x minus 2y evaluated at xn plus 1 yn plus 1 star Okay, so we have to calculate this y star first. Okay, well, let's do that. So y1, so 1 meaning step 1. So y1 for Euler's method is y naught, the initial condition, plus h times the function f evaluated at x naught, y naught. So x naught minus 2 times y naught. Okay, well, the initial condition y naught is 1. The step size is 0.1, h equals 0.1. X naught is 0, minus 2 times 1. I don't know why there's not a times there. That says it should be 2 times 1. Anyway, so that is 0.8. Okay, because we get 0 minus 2 times 0.1 is 0.2. So 1 minus 0.2 is 0.8. So for the improved Euler's method, we do the same thing actually to start with. So in fact, I can already tell you that this is going to be 0.8 because the predictor part of the improved Euler's method is exactly the same equation as Euler's method. So I in fact also get 0.8 here. And that's pointed out here that these are exactly the same. However, the second part of the improved Euler method, the correction part, is we take y naught plus h over 2 times the function evaluated at x naught, y naught, so x naught minus 2 times y naught, plus the function evaluated at x1, y1 star. So x1 is 0.1, because we're taking one step of size 0.1, minus 2 times y1 star, which we just said was 0.8. So I'm not sure why the numbers have gone funny here, but this should be 0.1 minus 2 times 0.8. Okay, so if I evaluate that, then that turns out to be 0.8250. Okay, so the prediction using Euler's method, y1 is equal to 0.8. The prediction using the improved Euler method is y1 equals 0.8250. The exact value found from the analytical solution up here, so if I put x equals 0.1 in this exact analytical solution up here, the value of y corresponding to that is 0.8234. So clearly you can already see the improved Euler method is significantly more accurate than the Euler's method. So we can calculate the error in each approximation. So the error in the Euler's method is 0.8 minus 0.8234. So the Euler method approximation minus the exact solution, the absolute value of that, is 0.0234. Using the improved Euler's method, that difference between the predicted and the exact solution is significantly smaller. In fact, it's more than 10 times smaller. So 0.0016 is more than 10 times smaller than the Euler method value of error of 0.0234. So even though the improved Euler method was more work, we had to first calculate the star value, and then we could calculate the actual predicted y1. So even though we had more work to do with the improved Euler's method, the error is actually more than 10 times less than that of the Euler method. Okay, let's look at another example now. So this ODE y prime equals 4x minus 2y with the initial condition when x equals 0, y equals 2. Okay, so the exact solution, again, you can figure out the exact solution to this equation. It's a linear equation, so you can solve it using an integrating factor. But the exact solution to this ODE, or this initial value problem, is 3e to the negative 2x plus 2x minus 1. So the question asks us, we want to approximate y when x equals 0.5 using the improved Euler's method with h equals 0.1 and h equals 0.05. So, okay, if h equals 0.1, we'll have to take 5 steps of the improved Euler's method. If h equals 0.05, we have to take 10 steps of the improved Euler's method. Okay, we want to also verify that the global truncation error for the improved Euler's method is the order of h squared. So this is going to be quite a lot of work, and well, it would take me quite a long time to write this out on a piece of paper. So actually, I'm going to set up an Octave script to do this for us. Okay. So I will move over to Octave Online now. Okay, so we're over here at Octave Online, and I've just written out some instructions just to help us out, save us switching between windows. So here is just sort of my version that I've written out of the improved Euler method, and of course the problem that we're trying to solve. Okay, so we're trying to solve dy by dx equals 4x minus 2y. We had the initial condition at x equals 0, y equals 2, and we're trying to solve x equals, we're trying to find the value of y when x equals 0.5. Okay, and so here is the improved Euler method here. So we have the y star here, and we have the update for y here. Okay, so the function f here is of course the right hand side, 4x minus 2y. These commands here, clear all, close all, and CLC, I've just added those to make sure there are no latent variables stored. So here you can see I have y and answer, ANS, stored. So if I add these commands, that will clear all those commands. Okay, so what do we need to do to solve this problem? Okay, so the first thing we should define is the step size h. So the first step size we're going to look at is 0.1. And I'm just adding this text here, it's just like a way of commenting your code, just sort of helps it to be easier for other people to read. Okay, so I've got the step size h equals 0.1. Let's also add our initial conditions here. So xn equals 0, yn equals 2. So, well, actually, let's call it y0, actually. x0 and y0 equals 2. Okay, so I just wrote my initial conditions down here. So what I want to do now is create a vector x, capital X, which is going to be equal to all the values of x that we will be using. Okay, so we're going to start at the point x0. I'm going to take a step inside of size h, and we're going to finish when we get to x equals 0.5. Okay, so if I save that now and run that, we should get a vector of between 0 and 0.5 in steps of 0.1. Yeah, okay, so here we go. I might actually just, okay, that doesn't work in Octave. Okay, I didn't realize that. Okay, never mind. We get a vector x, which is between 0 and 0.5. So you can see we have 6 entries in here, right? 0, 0.1, 0.2, 0.3, 0.4, and 0.5. What we want to do now is generate a vector y which has the solution of the ODE, or of the initial value problem, at these positions defined by x. Okay, so our initial condition x equals 0, so y in the first position we knew was equal to y0, right? So at the moment, x is this vector of length 6, y is just contains the initial condition 2. So we want to go through and update x and y. So there are multiple ways to do this, but I'm actually going to use a for loop to do this. So I'm going to create a new variable I, and this variable is going to go between 2 and the length of vector x. Okay, so this variable, the length of x I said was 6 because there are 6 entries in x. So this variable I is going to go 2, 3, 4, 5, 6. Okay, so that's 5 steps to fill in the 5 gaps that are missing in our y vector here. Okay, so I want to clear, I need to calculate this thing y star every step, every time, right? So I want to just, every time I start this loop, I want to just clear this y star. So this is ys is y star. Okay. Okay, but then I need to calculate y star. So ys, well, the equation for ys is y evaluated at the previous step, so I'm going to call that y, evaluated at the previous step. So I is the current step, I minus 1 is the previous step. So for example, when I is 2, this is going to be 2 minus 1 is 1. So we're going to be looking at the vector I, the one entry, or the first entry, which is y0. We defined that here. Okay, so ys, the y star is this y at the previous step plus the step size h times the function f, evaluated at xn, yn. Okay, well the function f is 4x minus 2y, so we're going to go 4 times x minus 2 times y. Okay, and remember we're evaluating it at the previous step, so it's at I minus 1. And similarly, we're evaluating y at the previous step, which is at I minus 1. Okay, so that's my y star step. So you could say this is the predictor step. Oops, should be a percentage sign. Okay, and then I'm going to calculate my updated value of y. Okay, and so that's using the second step, or the corrector step, of my improved Euler method here. So I have to calculate, to do this I take y at the previous step, so y at I minus 1 plus h over 2 multiplied by this f evaluated at xn yn plus f evaluated at xn plus 1 y star. Okay, so I'm going to have two things that I'm adding together here. Okay, so I'm just going to write it like this to make it clear what's going on. So this first one is going to be 4 times x minus 2 times y, and both evaluated at the previous step. So I minus 1. I minus 1. Okay. Secondly, I'm going to evaluate the function at xn plus 1 y star. So I get 4 times x minus 2 times y star. Maybe I'll make this a little bit wider. Okay, so for the second function f, x is evaluated at the current step, xn plus 1. So this is just going to be xii. Okay, and if I haven't made any mistakes, then I should be able to generate a table of the x values and the y values at the end. So let's just save and run this and see what happens. I made a mistake here. Okay, I've used, this is good. So you can see here I've used square brackets when I should have used round brackets. Okay, so that was my mistake. Everybody makes them. It's normal when coding, but let's change that and save it and run it again. Okay, so it's just running through. And now if I just make this wider here, so the answer that we're getting here, this first row is the x values, the second row is the y values. So you can see this is the initial condition, x equals 0, y equals 2, x equals 1. The improved Euler's method says that we should be 1.66. X equals 0.2. The improved Euler's method says that y should be 1.41, all the way through to 0.5. When x equals 0.5, y is approximated to be 1.1122. Okay, excellent. So if you recall, we were asked to do this for step size h equals 1, and then step size h equals 0.05. Okay, so we've done that for step size h equals 0.1 now. Let's do the same thing, but for step size 0.5. And so the lovely thing is, the way I've written this code is I can change the step size, and I have to change nothing else in this code. So all I have to do now is save and run that code. And so our prediction was Previous prediction was 1.1122. Let's see what happens if we half the time step there. Sorry, half the space step h. And I may need to add some more time. Okay, so of course I had to do double the amount of work. I had to do 10 steps now. So you can see we've gone from our initial condition, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. And so previously we had 1.11 as our prediction using a step size of 0.1, whereas now we have 1.1056. So we're going to hope that that is more accurate. Okay, but the point is, we've written a code here. We've written a code here in Octave to solve our initial value problem. And so if you think about it, if I wanted to adapt this code to solve some other initial value problem, well, I can change the step size here. I can change the initial conditions here. I can change the end value of x here. And then really the only thing left to change is the right-hand side, the function f, which is hiding in all these brackets here. So in theory, you should be able to take what I've done here and adapt it to any other problem you're working on. Okay, so now we can change the step size. Well, maybe let's just for fun really reduce the step size and just see what happens. So if I save and run that, well, it starts. You can see we've got to do a lot more steps here. We've got to do 50 steps now. I'll add some more time. Our solution should be much more accurate, in fact, using a smaller step size. Okay, great. So here the solution is saying when x equals 0.5, y is 1.1037. Okay, for the step size 0.05, this was 1.105 something. So we're getting more accurate as we reduce h, but it's a lot more work. Okay, so let's just check the truncation error in the improved Euler's method now. I'll go back to PowerPoint. So now we've approximated the value of y when x equals 0.5 using two different step sizes. So just to sort of summarize that for us, we generated with h equals 0.1, we did 5 steps of improved Euler, and when x was 0.5, y was 1.1122. So I've got a lot more decimal places here, of course. When I halved the steps size there, h equals 0.05, we had to do double the amount of work. I had to do 10 steps here to get down to x equals 0.5, but I got a number that I expect to be a lot more accurate. Okay, well, the exact solution when x equals 0.5, I can use that in my exact solution up here, my analytical solution up here. I can put x equals 0.5 into that, and if I do, I get y at 0.5 is equal to 1.1036. Okay, so you can already see that halving the step size has increased the accuracy. Okay, so the error for step size h equals 0.1 is the exact solution, 1.1036, minus the numerical solution, 1.1122, which is 0.0086. If I half the step size, the error at h equals 0.05, the exact solution minus the numerical solution, 0.02. So you can see it's at roughly 4 times smaller. Right, so in green here is the larger step size and purple is the smaller step size. If I take the ratio of these two errors, so 0.0086 divided by 0.002, it's just over 4, okay? And so this is close to the theoretical global truncation error, which I can write as some constant times h squared, because we said that the improved Euler's method, the global truncation error was h squared, was order h squared. So if I look at the ratio of h squared over h over 2 squared, well, the c1's the constants cancel. The h squareds are going to cancel. I end up with 1 divided by 1/2 squared, which is a quarter. So I get 1 divided by a quarter, which is 4. Okay, and we got 4.3. So in fact, it's better than the theoretical. Okay, so we've verified now that the global truncation error for the improved Euler's method is order h squared. Let's take another look at another example. Dy by dx equals x plus 2y with a initial condition when x equals 0, y equals 0.25. I'd like to solve this using the Euler and the improved Euler methods in Octave, just to show you how much more accurate for the same step size the improved Euler is. Okay, well, yeah, let's decide how many steps we're going to take soon. Let's go to Octave Online again. Okay, so I've just taken our improved Euler method code from our previous example and just modified it to solve our current example now. So dy by dx equals x plus 2y. Our initial condition is when x equals 0, y equals 0.25. I decided that we'll evaluate x at 1.0. I've still got my my pseudo code for the improved Euler method here. I decided to take a step size of 0.1. I modified my initial conditions here, so x naught is still 0, but y naught is 0.25, so I've modified that here. My x vector here, now we're still starting at 0, and we're still going in step sizes h, but now we're going to x equals 1.0. Okay, so I modified this. And then the only other thing I've modified here is the function f. So the f in this y star and the two f's in the final corrector equation. So instead of 4x minus 2y, now I have 1x plus 2y. 1x plus 2y, 1x plus 2y. So really minor modifications for this improved Euler's method for this example. And you can see I've already run that here actually. So the improved Euler method gives us this solution. Maybe I'll type it in here. When x equals 1, improved Euler says y equals 2.9023. Okay, so we're gonna come back to this later and check it against the exact solution. But first I want to calculate the same solution to the same ODE, but using the Euler method. Okay, so I've written out some code here. Now we're using the Euler method to find the solution to the same initial value problem. But now Euler method, of course, has a slightly different way to calculate. I've still got the same step size, the same initial conditions, and the same x vector here. So now I just need to do the iteration part of it. So for I equals 2 to the length of vector x, I don't need to calculate y star anymore. I can just directly calculate the updated value of y. So the updated value of y is equal to the old value of y, so I minus 1, plus the step size h, times the function f. Okay, and the function f was x the function f is evaluated at the previous step, xn, yn. So x plus 2 times y, both of those evaluated at the previous step. So I minus 1. And again, I'm going to output my solution vector. So let's check, let's run that, make sure I haven't made a mistake. Okay, great. So this looks a bit silly. Hang on, what's going on here? If I widen that. Okay, I've used the wrong, this should be x semicolon y. So we'll save and run that again. Okay, that's better, that's better. So now using the Euler method, we say when x equals 1, y equals this thing. So when x equals 1, the Euler method says y equals 2.3459. Okay, and just for the comparison, let's just go grab the value from the improved Euler. So when x equals 1, the Euler method says y is 2.3459. The improved Euler method says y is 2.9, basically. And so this is quite a big difference, right? So let's just also, when x equals 0.1, the exact solution is y equals something. Let's get some help from Wolfram Alpha here to find out what the exact solution is. So if I come over to wolframalpha.com, all right, dy by dx equals x plus 2y, with the initial condition when x equals 0, y equals 0.25, Wolfram Alpha tells me that the exact solution is negative 0.5x plus 0.5 times e to the 2x minus 0.25. So let's open up a tab with this equation and say, what is this value at x equals 1? And lo and behold, I get the value of 2.94453. 2.94453. So you can see here that, well, in fact, the Euler method for this particular example is really awful, in fact. That is a long way away from the exact value. But the improved Euler method, in fact, is pretty good. It's within, it's within 2%, I think, around about 2%. Okay, so the moral of the story is the improved Euler method is a significantly more accurate method than the Euler method. You need to know, well, for your assignment, you need to solve these types of problems using MATLAB or Octave. For your test, you'll be asked to do somewhat, for test 3, so the exam, you'll be asked to do somewhat simple, maybe 1 or 2 steps of the Euler or the improved Euler method, similar to past year's exams. So you might like to check those out before your exam. Again, if you have any problems, please let me know, and I'll see you in the next lecture.